We would like to find a surface area of a cone, and precisely we want to prove in this video the surface area formula of a cone. And when we're talking about the surface area, we're talking about a lateral surface area. The lateral surface area, not the top circle of the cone area, but the lateral surface area. Basically the surface area of the circular part of the cone, the circular surface of the cone, basically. Okay, because the top circle there, it's a flat surface, right? And for this reason, to ignore it, we're going to say that it's an open cone. Okay, if it's an open cone, that is, the top is open, there's nothing covering that circle there. Thus, the surface area only covers the lateral surface area, right? We're not talking about the area of the circle, but just the circular surface of the cone. That's what a lateral surface area means. Okay, so to do that, we're going to need to use a double integral. And as you can see, the surface area formula for the double integral is integrating over a region that we're going to determine. And we're going to have a square root in the integrand, and inside the square root we're going to have the function of the x and y at the same time. So we're talking about multi-dimensional function, right? Speaking of multivariable function, to be precise, of x and y, and we're talking about also finding the partial derivative with respect to x of that multivariable function, and then squaring that partial derivative function with respect to x, and then adding the partial derivative with respect to y of the multivariable function xy, and then square it, and then add the 1, and that would be the integrand under the square root, okay, dA. Okay, so to do that, as you can see, we need to derive a function, a multivariable function that serves to show you the cone. Okay, we need to find a function that expresses a cone in 3 dimensions, because as you can see, this is a 3-dimensional graph. We have an x-axis, we have a y-axis, and we have a z-axis, right? So this is three-dimensional. So 2 dimensions will be covered by the x and the y, and the third dimension, which will express in terms of the x and y, will be the z. Okay, so to do that, we use the equation of the cone. Okay, this is the equation of the cone that we can use, and then we can solve this equation in terms of z, right? We're going to solve it for z, so that we can then find the partial derivatives with respect to x and with respect to y. We square those functions, we plug them inside the square root here, and then we're going to see what we're going to do with the integration after. So as you can see, the a squared, the b squared, and the c squared, the a, b, and c respectively, serve as components of this cone. The a serves as the component which is the radius of the cone. As you can see, what I drew here is the xy plane projection of the circle of the cone, okay, that you can see there. Because every cone ends with a circle, right? That's where it stops. And this circle, if you project it onto the xy plane, you will get exactly the same circle here on the xy plane. So the a stands for the distance from the origin, because that's where we drew the tip from, the tip of the cone from. So the distance from the origin to this vertex here is going to be precisely the radius of the cone, right? So we're going to denote that radius as r subscript c, and since a is squared, we're going to square that. And as you can see, the r subscript cone is part of a surface area formula that we need to derive using integration, right? So we have that part. Now the b squared serves as the same distance, but in the y-axis direction, right? From the origin, you're going to go all the way until you reach the vertex here of the projected circle onto the xy plane you see here. So it's going to be also the radius, right? Because we're talking about a circle. The radiuses in the circle match, right? So they have to be the same length. We're not talking about ellipse, we're talking about a circle. Okay? So it's also going to be r subscript c, the radius of the cone, squared. Now the c is a little bit more tricky, because the c is the third component that makes up the three-dimensional figure. Because right now what we have is two dimensions, x and y. We need the third dimension, z, right? So the c, naturally, as you probably have guessed, will be the height of the cone, right? So the c will account for the height of the cone, okay? So we're going to replace the c with simply the h. And as you can see, the h is also taking part in the surface area of the cone, lateral surface area of the cone formula. So h replaces the c. So as you can see, we have everything we need here. The only thing we need to do now is to solve this equation for z, right? And I'm not going to solve it. I think you should do this on your own. I'm just going to write out what the z is equal to. So the z, if you solve for z squared, this is what you should get. So z squared should be equal to h squared times x squared plus y squared divided by rc squared. Okay? So this is what you should derive. Now the problem is, which z do you use? Because if you square root and solve for z, because you can't just solve for z squared, you need to solve for z, right? So in order to solve for z, you realize that you have to take the square root on both sides. If you take the square root of both sides, you will have a plus minus inside the square root. Now here's the deal. As you can see, the z is drawn in such a way that there's a positive z-axis and there's a negative z-axis below the origin, right? So notice that we're talking about a cone drawn up because it opens up from the origin, right? The tip of the cone is right at the origin. That means we're talking about only positive z values, right? We're not going below the origin. So for this reason, when we're talking about plus minus, we don't need the minus in front of the square root. So we're just taking one solution of the z and not the second one. Right, so what I'm talking about is that z is equal to the positive square root. There's a positive sign in front of it. We don't need the negative. And inside the square root, we're just going to square this whole thing, right? So it's going to be h squared times x squared plus y squared divided by rc squared. Right? And I'm square rooting everything, right? The bottom too. Don't think it's just the top. It's the bottom as well. So now that we found the z value, realize that this means that the f, the function of x and y, is going to be precisely the z. Right? So what I want to do, I'm going to write the z so that you understand that it's going to be the function, the multivariable function of x and y. Okay, and that will be equal to this. Okay, so I'm going to write it down. H squared plus x squared plus y squared over rc squared. So now that we have that, we need to find the partial derivatives in order to use the surface area formula for the integrand of the double integral that we're going to use. So now the partial derivative, let's see. So we need to first differentiate with respect to x. Okay, so derivative with respect to x, the partial derivative with respect to x, we'll only differentiate the x squared, right? Y squared is going to be treated as a constant in a partial derivative, so that's going to be 0, right? So and basically, before we do that, let me actually erase that for a second. I want to simplify this a little bit more. As you can see, h squared over rc squared can be taken out because the square root of the h squared is h, and the square root of the r subscript c squared is rc, right? Because both of these guys are squared. Square rooting them means we can take them out. So basically what this means is we're going to get h over rc. And that's going to be a much simpler square root, right? So it's going to be basically x squared plus y squared inside, right? X squared plus y squared. Okay? So that's going to be easier to take care of. Okay? So now the partial derivative that we're going to have is going to be this. okay, with respect to x. So notice that this is treated as a constant. So we can copy that, put it in parentheses. It's not going to change anything, right? It's constant. When it comes to constant, you just keep it that way. And this x squared plus y squared is raised to the power 1/2, right? Taking the derivative of this means 1/2 comes down, right? So 1/2 comes down, and then the fraction is on the bottom we're going to have x squared plus y squared inside the square root, right? Because the resulting power will be negative 1/2 for this, right? For the x squared plus y. So negative 1/2 means the square root is on the bottom with inside x squared plus y squared, right? And on the top, of course, you're going to have the chain rule at play because you're going to just differentiate both of these, but you know this is treated as a constant because you're differentiating with respect to x. So y squared, the partial derivative of y squared with respect to x is just 0. So you're just differentiating this, and you're going to get 2x, right, using the power rule. So 2x goes on the top, and that's it. Okay? So that would be, and notice what happens is automatically assume these two cancel out, right? Because the 2 on the top, 2 on the bottom, they cancel out. So you don't see that anymore. Now, in the same way, the partial derivative with respect to y for this multivariable function is going to be the same, right? The h over rc is written again. And then here we're going to have, I'm not going to write 1/2 and I'm not going to write the 2. I'm just going to write y over x square root of x squared plus y squared, right? It should make sense to you that this is what should follow. Okay, so now that we have that, what are we going to have inside? What are we going to have inside now that we have that? So let's understand. So we need to square both of these partial derivatives so that we can write it inside the square root of that formula for the surface area in the integrand. So if we square this, let's square that for a second. So if we square this, we should basically get the square of this, right? So it's going to be h squared over rc squared. So again, squaring this back. And then here we're going to have x squared. And this square root is being squared, right? So the square root is gone, so it's just x squared plus y squared. Write that a little better. X squared plus y squared, right? And that's it. In the same way, of course, the bottom, I mean the second one, the partial derivative with respect to y being squared will be the same thing, except the top will be replaced with the y squared, right? So we're going to have h squared over rc squared and then here we're going to have y squared over x squared plus y squared. Okay, so now that we have that, we know what we're going to put in, right, inside this formula. So let's think about what this integral is going to become. So we're not going to determine the limits of integration yet. We're just gonna well, actually, let's see if we can. So here's the thing. So we're going to have inside what? Let's write a 1 first inside the integrand. 1 plus, and then let's write the partial derivatives being squared. So this one is h squared over rc squared. Okay, so let's write that h squared over rc squared. Okay, and notice that in both cases, when you're squaring and when you're adding them, basically you're adding these two. These two, right? So you're adding these two, and both of them have h squared over rc squared as common terms. So we can leave that out, and we can just add these two guys together, these two fractions. X squared plus y squared, and both will be divisible by x squared plus y squared, right? So basically, this leads to being the numerator and denominator exactly the same, which is great, right? Great news. Okay. And yeah, so I'm just going to leave the limits of integration for now unknown. I'm just going to write r still. And this is going to be dA. And here's what we're going to have. So notice that immediately this cancels out because this is the same thing. The numerator and denominator are the same. So what we have as a result is just what? We basically have just this under the square root. Okay? So what we have as a result is just 1 plus h squared over rc squared. Okay? dA. Okay? And now let's talk about the limits of integration and what we're going to replace the dA with. Okay, so now that we have that, notice that first of all, this thing is going to be constant. Square root of 1 plus h squared over rc squared is going to be constant. Okay, because h and rc are constant, and so is 1, right? So the square root of that will give you a constant. But let's rewrite all of that just in case. Notice that we can combine this into a single fraction. 1 plus, so rc squared plus h squared over rc squared will be the entire fraction. Right? Because you multiply the 1 with the rc squared divided by rc squared, that becomes rc squared over rc squared, right? That's equal to 1. So basically what we're going to have is this. We're going to have rc squared plus h squared over rc squared. So now what happens is we're going to take this out and write it to the left of the integral, outer integral, because this is constant. And notice that we can take rc squared out because the square root of the rc squared is just rc. So you can just write it as 1 over rc. Okay, and then we can write the square root. And then we can write the square root, and this is going to be rc squared, which I'm going to write in red. Rc squared plus h squared. Right? So this is what we're going to have. So now let's talk about the limits of integration here. So now the best thing that we need to do, we need to convert this dx and dy integral into a polar coordinate integral. So as you know, polar coordinates deal with the angles and they deal with the radius. The outer integral will deal with the angle of rotation, and the inner integral will deal with the radius. Okay? So now here's what we're going to talk about. And why we're converting? We're converting because definitely the cone is a circular figure, right? We know it ends with a circle, as you can see. It's definitely circular. It consists of infinitely many circles like that and radiuses, respectively, right? Because these, basically, as you go higher in the cone, you're adding up more larger and larger circles until you basically end up at the largest circle on the top, for which the radius is the RC. So now the outer integral is going to be integrated from 0 to 2 pi. And how do we know that? Because we start, let's say at this point, we have to go all the way around the circle so that we make a cone, right? We will have to go from 0 to 2 pi to make up the entire cone when we're talking about rotation. And now the second one is, of course, the distance, right? The distance from the origin to where we stop, right? Which is going to be the edge of that largest circle. So as I mentioned before, you're basically adding up infinitely many circles as you go up higher in z value, and you're increasing the number of circles until you get to the largest circle, and that will have the radius RC. So you're naturally integrating from 0, from the starting point of the origin, where basically the radius or the circle itself is invisible, right? That's why you start at 0, and then you go all the way up until you get to the largest circle possible, right? Because you're putting up circles on top of the other infinitely many times until you get to the highest circle, the largest circle, which has the radius RC, right? So the radius is from 0 until you get to the highest value of the radius, which is RC, the constant radius of this cone. So we're going to write RC. And of course the variable, because we're definitely talking about a variable, first of all there's a 1 times, because we took this outside the integrals here, because this is a constant, so it's going to be 1 times, and now it's going to be r dr d theta. Okay, r dr, as you can see, it's not just dr, remember it's r dr, and r is a variable, of course. We just talked about the radius as being infinitely added on top of each other, the circles, until you stop at the very top, right? So this is the r variable, right? It takes into account all the radiuses of all the infinitely many circles that are below this largest circle, right? That's why r is a variable and rc is a constant. It's just the radius of this greatest circle that you see on the top. All right, so these two are different things. The r is a variable that accounts for all of the circles below the largest circle that make up a cone, but the rc is just the radius of the top circle, the largest circle. All right, so now that we have that, it's going to be fairly easy to arrive at this formula. I'm just going to work rather quickly. So we can just copy down 1 over rc, and then square root of rc squared plus h squared. And of course we're integrating the r first, so it becomes 1/2 r squared using the power rule. And the 0 doesn't matter, but the rc replaces the r, right? So it's just going to be 1/2 rc squared, right? So 1/2 rc squared. And then the integral here from 0 to 2 pi d theta. Okay. Now you can see we can cancel out the rc here. The power of 2 goes away. It's just 1 rc to the first power. And then we get, let's see, we can write 1/2 first. And then let's write rc. And then we can write the square root of the rc squared plus h squared. And then, so we integrate d theta, we just get theta. So we just 2 pi replaces the theta because 0 doesn't matter. Subtracting the 0 doesn't change the definite integral, right? So it's just going to be 2 pi, right? So it's just going to be 2 pi. So now let's see if we can cancel out more stuff. As you can see, the 2's go away. So the 2 goes away, this 2 goes away, so we're left with pi that we can bring about as a first term, pi, and then we can write rc squared after it. Sorry, just rc because we cancel out the square, and then square root rc squared plus h squared. So as you can see, we've arrived at the exact formula we wanted to by proving it using double integrals. So I hope this was fun. I hope you understand how to do this now. Thanks for watching. See you in the next video.